Okay, so good morning, good afternoon, good evening, everyone, wherever you are. Thank you very much for joining us this afternoon for this very interesting webinar that is being organized by the Interdisciplinary Center for Circular Economy of Mineral-Based Construction Materials. So today we're going to have a very interesting presentation from colleagues from industry. And their talk is on transformation of London clay into construction resources. And this project is named the Real Project. So perhaps many of you have been in many webinars in the past, but again, we would like to have some brief housekeeping. So we would like to remind our attendees that this meeting is being recorded. So if you do not wish to appear in the recording, please keep your camera off. So the presentation will last between 15 to 20 minutes. And afterwards, we will give the opportunity to our attendees to make any questions or make any comments that you wish to share with us. So I will appreciate if people can raise their virtual hand, or you can also please feel free to put your comments in the chat. We will do our best to cover as many questions or comments as we possibly can. And finally, just a comment that the recording will be made available. I will be emailed to you and shared on social media, hopefully next week. So also finally, please remember to keep your microphone off during the presentation, just to avoid having some background noise while our colleagues are presenting and sharing the project. So it is my great pleasure today to introduce these fantastic speakers that will be sharing with us the research. So first, I would like to introduce Athena Papacosta. Athena is a sustainability, a whole cycle carbon consultant for the built environment. Currently, she's leading on sustainability for the main works civils contract for HS2 London tunnels. And also I would like to introduce Fraculis Cannavaris. So Fraculis is an Arab's award-winning concrete and cementitious materials expert with experience in materials specifications, low carbon concrete, simulating, testing, designing, monitoring concrete structures, and with contributions in more than 250 projects worldwide and with more than 40 publications. So welcome, Athena and Fraculis. Now it's over to you.
Lovely. Thank you, Susan. I will quickly share my screen and make it start. So, right. The pains of having too many windows open. So there we go. I hope that you can see my screen all right. So as Susan mentioned, we're going to have a quick recap, a quick summary on the so-called REAL project, which is the feasibility study we're running as part of the HS2 delivery contracts to look into how London clay spoil can potentially be transferred into useful construction resources. So bit of background on that, which may as well be common knowledge to most of the audience. Growing construction globally means growing demand for concrete. That is one of the building blocks of construction. Same time, increasing sustainability and planetary change challenges in our environment, with the climate change being one of the most salient ones in our days. These in turn dictate more low carbon, more environmentally friendly solutions. Looking at these two in combination, in conjunction, the need for robust concrete materials to essentially keep support global growth and also go side in side, go hand in hand with sustainable development and essentially the provision of lower carbon alternatives in order to essentially meet the requirements to reduce and minimize our emissions and essentially reach net zero by 2050, we're faced with a particular problem in the world of concrete. We have to look into solutions with alternative cementitious material, given that cement is the most carbon intensive constituent in our concrete. So moving on, when we're looking into infrastructure projects specifically, moving away from concrete as a whole and looking at infrastructure projects specifically, there's also a number of major challenges, as you see on your screen, that have to do with obviously the overarching environmental sustainability and climate change aspects that revolve around overall resource efficiency and carbon emissions, excavated material management, which is even more, it can get even more tricky when we're dealing with urban and densely populated areas. This obviously leads and links into road traffic congestion, air quality considerations, so on and so forth. There's also obviously the challenge, especially when we're talking large scale with raw material availability, there's affordability, there's also upskilling and innovation that is in dire need in the construction industry. So very broad brush lines with regards to infrastructure projects specifically. Quick introduction to our specific infrastructure project that is essentially hosting this feasibility study. We're looking at HS2, is a key infrastructure project, railway project currently underway in the UK. Phase 1 is down here linking London Euston to Birmingham. Few more details on the left-hand side. So currently we're talking essentially this stretch down here, and our particular contract is linking London Euston to essentially the northwest end of London. And as you can imagine, it being so very densely populated with not much space above the ground, our project consists of mainly tunneling works, and hence excavation material is one of the key aspects we have to deal with. So zooming into our stretch, the stretch that we're dealing with, this is just a more detailed overview of the project, which is pretty much tunneled from the beginning at the Euston station all the way pretty much the end, where trains come out of the ground for a very small stretch, and then we're handing over to the next contract. So as you can imagine, around about 40 kilometers of tunnels, associated shafts, a lot of excavated material. HS2, as the client and as the entire program owner, they in their own right have very high ambitions with regards to the environment. I'm not going to dwell on it too much. I'm just going to highlight that there's specific rigorous considerations, targets, and requirements, specifically around carbon emissions and nature recovery, including resource efficiency. So there's also a net zero carbon plan available in the public domain for more details, so on and so forth. All this just to stress that there is a strong drive over and above just the ambitions of our own joint venture and our own parent companies from the client as well. That is very important and is supporting innovation projects like the one we're going to talk about. So a bit more specificity on the client drive. So focusing on what our specific, let's say, parameters are, we're talking around about 5 million cubes of excavated material for our project. Most of it, given the location, is expected to be London clay. So main challenges we have to deal with is obviously waste management, excavated spoil management, as briefly touched upon just earlier. And of course, we have a huge demand for concrete to build the tunnels and the auxiliary structures and the heavy geotechnical structures to essentially support the function. So concrete comes into play in terms of quality, availability, and of course, its environmental impacts, its embodied environmental impacts. So key objectives when we started looking into this project, this feasibility study, had to do with essentially these main challenges. So we zoomed into how can we make the most out of our excavated spoil, that is London clay in this particular case, so essentially waste repurposing. And should we be able to make something useful out of it, in this sense, we would be offsetting the use of imported materials with site-borne ones, and therefore avoiding waste and the associated disposal, with the accruing benefits around resource efficiency, carbon emissions reduction, potential for cost savings and improved air quality, and less nuisance for the surroundings. So following basic circular economy principles to essentially make the most out of what would otherwise be pretty much a waste stream, talking about our London clay excavated spoil. So, as mentioned already, we wanted to investigate the potential of essentially turning this excavated London clay into useful derivatives for construction. Main focus resides with supplementary cementitious material, that is calcined clay, and calcined London clay in a particular case. Frag is going to go through a lot more detail around calcined clay per se, but this is just to state that this is a main focus. We've looked into obviously expanded clay as well, that can be used as a lightweight aggregate, and I've actually had quite promising results on that front too. But with respect to our particular project and the scale of the global challenge, concrete and therefore the supplementary cementitious side of things, the calcined clay, is essentially bearing the lion's share of our attention and focus at the minute. So moving on, again, very quickly, key benefits that I've already touched upon around muck-away reduction, resource efficiency, embodied carbon reduction, and potentially cost benefits and legacy, as well as technical upscaling advantages. So in order to look at this in more detail and more systematically, we have essentially drafted this modular project, this modular feasibility study, to delve deeper into the potential of London clay. So as you can see on the screen, essentially the project, the feasibility study, is split into two main stages, 1 and 2, and stage 1 in its own right, the proof of concept stage, is again in turn split into 2. So stage 1A completed already. We call it the raw material feasibility study, London clay material characterization, where we effectively have looked into how much and what is already out there with regards to London clay in particular, and its potential, not just the geological background, but also its potential with regards to these key strands, these key targeted outputs that we're looking at around supplementary cementitious materials and potentially lightweight aggregates. And during that stage, we tested several samples of London clay in essentially with regard essentially to the material characteristics and whether they would actually constitute good source for calcined clay. So we tested around about 10 samples from across the stretch, and got pretty promising results, which allowed us to move into the stage 1B that is currently ongoing, which is the actual concrete feasibility study, where we essentially got bigger quantities, bigger amounts of London clay, this time from our works, to rerun material characterization to essentially verify the prior intelligence, and therefrom fabricate bigger quantities of the London clay, the calcined supplementary cementitious materials, and run tests at lab scale with paste and mortars, concrete paste and mortars, and as currently underway, run tests with actual concrete samples, fresh and hardened, run the tests, and essentially conclude whether we can move into what is the big idea, if you like, the aspiration to move into a bigger scale site trial, where we will actually attempt to produce bigger quantities of such supplementary cementitious material on site and use in our own concrete applications. So we got a team that is star-studded, which consists of material experts in-house from SES Railways, as well as support, like myself, from the environmental and sustainability side of things. We also have expertise from our design partner that sits within SES, and FRAG is representing that expertise in our call. And we're working with recognized experts, academic experts on the field of calcined clays, like EPFL in Lausanne. We've worked with UCL before, and obviously we got Susan from University of Leeds. And they're all doing work in this particular field. And we also have a couple of industry partners that are helping us out with the industrial processing of our materials, of course, under the auspice of High Speed 2. And on this jolly note, I'm going to pass on to Frag. Keep it moving.
Okay, many thanks, Athena. So hello, everybody. That brings us to recapitulate on the two main problems we had to face when we were thinking of about this main issue, and that we're still facing. This type of issues are very much relevant to all types of infrastructure. So number one, we had to reduce the embodied carbon of concrete because of all the things that Athena mentioned. We know that significant volumes of concrete will be used on the project, and we cannot 100% rely on traditional supplementary cementitious materials, predominantly GGBS for the location of that project, because they are depleting. Other supplementary cementitious materials, such as those listed there, fly ash, silica fume, metakaolin, are not appropriate for large-scale implementation, and non-standard solutions, for example, alkali activated materials, do not immediately solve the problem. Again, there is the scale issue, and also most of them, at least the commercialized ones in the UK, utilize already depleting supplementary cementitious materials. And the second main point and problem is that we have to manage the excavated London clay. 5 million cubic meters of clay is a substantial volume. So we need to find an efficient way to manage that type of excavation. And as we say, convert it from a low value application to a high value repurposing. We have experience from previous major infrastructure projects where high carbon emissions were associated with disposal of excavated clay. Next slide, please. Yeah, sorry, maybe we'll have some delay, but that doesn't matter. So when we're thinking back about the possibilities, I think it was like already 4.5 years ago, we're thinking, what can we do with that clay that it's going to be excavated? We're aware of previous work in terms of using that particular clay to produce expanded clay aggregate, not necessarily for using concrete, but for other applications. But we had the idea of using actually the clay to investigate it further and calcine it to use that supplementary cementitious materials. So a lot of people and partners, when they hear this idea, they were not very supportive or very happy, but it wasn't something that it came out of the blue to us. We had past experience and past evidence of clays being used as supplementary cementitious materials. Calcined pozzolans from the ancient Roman and Greek times. In Brazil and generally South America, calcined clays were used in massive concrete structures like dams to fill large concrete volumes. We have been using metakaolin. We have experience in accumulated within an expert lime. Oh, sorry. Could you please mute your microphones? Thanks. Within a Rylam group, TC2A2CCL. As I said before, it's not the first time that someone wants to produce expanded clay lightweight aggregates. So it was deemed prudent to investigate that avenue of London clay to be used for calcined clay, for using concrete and expanded clay aggregate. Next slide, please. Right, so you've seen this slide before, but I will like to get you in a stepwise process in terms of what we have been doing to date, starting from stage 1, which was the raw material characterization to see what are the properties of raw clay, what are some key parameters that affect the activities of clays and their suitability for using in concrete as a supplementary cementitious materials, and how that study was complete and evolved to actually producing concrete mixes for the project. So let's start from stage 1A, which is material characterization. Next slide, please.
Sorry about that. It takes its sweet time for some reason.
That's okay. So in terms of characterization, we had to carry out certain tests to find out more information on the raw and calcined London clay specifics. Raw include liquid limit and plasticity index. These are typical tests done in soil characterization, particle size distribution, XRD and XRF. Apologies for the typo there. Isothermal calorimetry and thermogravimetric analysis to determine some of the reaction properties, and of course calcination time, which is relevant to calcining the clay for use as a supplementary cementitious material. Porosity and expandability testing to see how it behaves for expanding clay aggregate. So the key parameters in this case that we want to find out was the clay reactivity, and this is indicated from determining the kaolinite content in clay. Sorry, could you please go back one slide?
Sorry about that. I was trying to be proactive.
So the key parameters for supplementary cementitious materials for clays is the kaolinite content, because this is an indication of the reactivity of the clay and how feasible would be to use the clay in concrete. And the parameters which are key to expand clay aggregate production is the porosity and expandability. So now we're moving to the next slide, where we see some of the first results for, that we obtained a couple of years ago. So to give a little bit of context, kaolinite clays, kaolinite content in clays is used as indication for reactivity. 80% kaolinite and above is deemed very high quality clay to produce metakaoling, and we already know from literature that London clay varies between 10 and 20% kaolinite content, or even up to 30% in occasions, and it's highly variable. And this was confirmed from initial kaolinite tests on raw clay samples, as you see from the kaolinite content percentage column, approximately 22%. Next slide, please. And we moved on to calcine the clay at 800 degrees for 1 hour. And then we carried out some heat generation monitoring. This is through isothermal calorimetry tests, measuring heat evolved in paste samples. So let's say that, not to get very technical, the lowest the heat that is evolved during that period of testing, the lower the indication of kaolinite content. So comparing these results that we got with existing literature results, so in this figure, the green lines represent kaolinite contents, and the colored ones represent our samples. So we are in the lower end of that graph. We're approximately 20% or even 22%. So it's not something that we were not expecting. It is something that we confirmed after calcination. And this is considered a low-grade clay, low-grade in terms of its potential for using concrete. Next slide, please. So although we initially were a little bit concerned with the results we got, we examined the literature and we're very encouraged, let's say, to find something. For example, in this graph, for 20% kaolinite content, that's on the x-axis, in the LC3 formation, which is a combination of calcined clay, limestone, and Portland cement, strengths of up to 40 megapascal could have been achieved. So we thought that this could be a good starting place for us to try and produce cementitious mixes with calcined London clay. Next slide, please. So this was what we did. Well, this was based on mortar samples with 35% London clay and 15% limestone, and the rest was Portland cement. And we found that we can reach up to 50 megapascals at 28 days for this particular test. So we thought, okay, that's promising. It's not high strength, so we can safely target low to medium strength concrete mixes. Next slide, please. And these are the initial results on expandability of the London clay samples that we got. And to sum up, we received samples that produce very good expandability and can be used as lightweight aggregate, although there are some, due to some embodied carbon issues and strength issues and limitations to lightweight concrete, we decided that our focus will predominantly be on the calcined London clay part. Next slide, please. So the summary for stage 1A was that we obtained satisfactory results in terms of using London clay as a cement substitution, but also if we want to produce lightweight aggregate, it is also possible. We knew that London clay had relatively low kaolinite content. We confirmed that with tests, but we also showed that it's not a limitation in terms of using in concrete. So we decided to start targeting highest impact potential applications, such as mixes, development of mixes with high replacement rates and low strengths. Next slide, please. So the mixes that we are targeting, they were aiming to minimize cement use, to use the absolute minimum cement content. For example, if we could use 280 or 240 kilograms per cubic meter, would be happy with it, and target the low strength applications, which means approximately 20 to 25 megapascals at 28 days, with cement replacement rates with the calcined London clay varying from 30 to 70%. And we would compare the results to our standard 50% GGBS mix, which is the mix that's been used as a control mix through. It's a minimum standard specified mix in HS2, at least for the contract that we are involved. Next slide, please. So again, we derived a large set of tests and systematized investigation. It started with raw material preparation, like collection of London clay samples. Athena herself went on site and dig out some clay from the excavation. That was a quite encouraging moment for the team, and then carry out the preliminary testing, some of microstructural tests we mentioned before, proceeded with calcining London clay, grinding in it, and now we're reaching all the way down to mix development, where here the University of Leeds and Susan teams helped us a lot. And currently we are carrying out trials on actual concrete mixes that are supposed to be used in the project. Next slide, please. So some of the initial results that we obtained, we were happy to see that we have more kaolinite content in the samples that we're investigating as part of stage 1B. We can say that this was somewhat expected due to the variability of London clay across the London basin area. And our works involve granulation, drying, heating, of course, calcining in a rotary calciner, and grinding to a specific particle size distribution. Next slide, please. So here are some evidence of the calcining process. Athena can play this wonderful video. If it doesn't play, doesn't matter.
Of
Okay.
course it does. It looks like a washing machine.
Yeah.
It's just much hotter than that. But yeah, this is the industrial process at this stage. So this is at the facilities at one of our external partners, where we send around about 400 kgs to be calcined and then ground. Shall we?
Yeah, okay. So this is all fascinating stuff, especially considering that they started as a crazy idea, and it's very nice to see that. So next slide, please. So our approach to mixed development first was, as we call them in binary blends. So we want to use just Portland cement and calcined London clay. And as we said, we're targeting low strength applications, 20 megapascals for 28 days. This represents a substantial volume of concrete that's going to be used in the project, like for walkways or for mass concrete applications. And starting from the least favorable mixes, for example, those with high water binder ratio, 0.6, and 50 and 70% replacement of Portland cement with calcined clay, and then start considering other water binder ratios and replacement levels as well. Next slide, please. As a secondary possibility that is probably going to be investigated in the future, we are also investigating ternary binding blends like the LC3 type of blend, where we combine calcined clay, limestone, and Portland cement, again, to see how the benefit from the synergistic effect of limestone is working with calcined London clay, and what kind of strengths we can achieve. Again, our target of strength is the same as before. Targeting the low strength applications, which are also the lowest in risk, considering that they don't contain any reinforcing steel in the project. Next slide, please. The essential testing that we're carrying out at the moment is to determine the fresh concrete properties. Workability is the key one, so we're carrying out slam tests, flow tests, depending on the workability that we want to achieve. Density, of course, and compressive strength, which is the key property at this stage. Next slide, please. What we were very excited to find, though, although we were targeting 20 megapascals at 28 days, this is a recent result from one of our recent mixes. We achieved 35 megapascals at 7 days, and that is a mix with a water binder ratio of 0.6 and 50% calcined London clay. So this is quite, I would say, surprising, and it is reinforced from other mixes and mix results that we have produced. So it's not an outlier. We got very promising results. We had to do a little bit more work in terms of achieving the required workability. We can see here from the slum test, the workability might be fine, but there might be a little bit of segregation. So we are working towards that. But strength-wise, which was our main concern, we're performing much well than what we initially anticipated. Next slide, please. So we are completing phase one at the moment, and we're finalizing the concrete mixes. We're still in the trial concrete mixing process. So we're heading towards phase two. So for phase two, we want to identify specific applications within the projects, which are now walkways and inverts and first stage concrete. These are all unreinforced concrete applications within tunnels, but also, given that we're getting good strength results, we might consider even structural concrete. So we want to adjust the mix and conduct additional testing, for example, some durability testing if required, get confirmation from SES and HS2, carry out a more detailed business case, including the sustainability and financial benefits to the project, get an on-site processing plant design completed, including the logistics, and liaise with concrete suppliers on batching options. We have come up with concrete performance monitoring plans that are already being used in the project, and that can be used for this particular concrete as well. Next slide, please. So going forward, what we had in mind was a very ambitious idea. We wanted actually to process the clay directly as it comes out from the tunnel boring machine at the excavation point, at the clay collection point. So we have designed a mobile clay processing facility that involves how many 21 different equipment, independent equipment, but interconnected, that starting from one, the clay as excavated is being inserted in the box feeder, which is part one, and then goes through the whole process with all necessary operations to, in the end, get just a powder, a red colored powder that is essentially suitable calcined London clay for using concrete. So this is the final stage, let's say, of our project, and we're hoping to start considering building that pilot in the next few years. Next slide, please. So to sum up, sorry if a lot of information is added there. We have indicated that although London clay has a low kaolinite content and is low in reactivity, we can still work around and use it as supplementary cementitious material in concrete. And this is not only paving the way for London clay to be used as a supplementary cementitious material, but for many other low-grade clays that can be found worldwide. We can also use it to produce expanding clay aggregate, although we already knew that to an extent. Preliminary tests with the LC3 type of binder reveal that we can go up to 50 megapascals. But now with the new binders we are considering, with 50% or even 70% calcined clay replacement, we may be able to achieve this high strengths with a binary binder formation like Portland cement and calcined clay only. We have an ongoing testing program, as I mentioned, that to finalize the concrete mixes. And if we are successful, which I think I'm allowed to say at this instance that we have good chances of being, at least in terms of technology, we can set the precedent for further earthworks projects to process their spoil, reduce landfilling, and reduce associated CO2 and resource depletion with infrastructure development. Thank you for your attention, and we open the floor to comments. Thank you.
Well, thank you very much, Athena and Faculis, for a super interesting presentation. As you might have seen in the chat, our attendees have been very active, asking a lot of questions. I'm afraid we just have 5-7 minutes for questions, so we cannot answer all of them out loud, but perhaps if Athena or Faculis, you would like to answer some of those questions in the chat, that would be great. So some of our speakers have raised their hands. So Mike Walker, you have your virtual hand up. Would you like to make a question to our presenters?
The first one who changed his mind. Let's see.
That's fine. So Theo Hanain from the University of Sheffield, in the chat, he placed a question asking, did you try to measure strength of cement samples with the same amount of replacement, but without calcining clay? Did you do that sort of experiment?
Yeah, Athena, should I take that? You want?
Yeah, please.
Yeah, okay. So we didn't do that because the clay is pyritic. So we want any pyrite to dissolve. So we didn't want to have any nasty, let's say, substances for concrete during the mixing process.
So another question is, well, one of the attendees says, thanks for the nice presentation. Is that a pure clay you received from the excavation?
Yes, I would say we have actually considered that. In fact, feel free to jump in wherever. This is something we considered since early doors when we were trying the different samples. It's generally fairly pure London clay. For the most part, though, of our excavation activities for this particular project, as Fag also mentioned, specifically, these are taking place via tunnel boring machines. And indeed, this means that the excavated clay will be mixed with conditioning materials, essentially the soil softening agents that essentially enable, enhance, and essentially make the excavation for the cutting head of the machine easier. However, these are usually literally foams that are pretty innocuous. So we have actually tested that during stage 1A of a project, and it turned out that it didn't affect, let's say, the purity and the results and the kaolinite content and anything that had to do with reactivity and the parameters that are relevant to our test for calcined clay. So not a problem. We're good in terms of that sort of purity.
Brilliant. Thank you so much. Another question is, do you have a sense of what might be the 56 days strength of the concrete that you're testing at the moment?
Through the roof.
No, just send us an email in 28 days. You will get an answer.
Yes, we hope that they continue straightening over time and behaving. I will say that's all fingers crossed for that. There are more technical questions regarding, for example, what is the particle size distribution of the clay, but this information is widely available in some of the publications for this particular project. So another interesting question perhaps is that calcined clays as binders are not included in current standards. So what will be the process to getting it into standards? Who takes the risk? How can we actually use them in practice?
Yeah, actually, I wouldn't say they're not included. They are included, especially in the UK. BS 8500 allows up to 55% of calcined or natural pozzolana within the concrete. So even if we go up to 70%, we can go up to 55% with this type of material, as long as, of course, it provides a reasonable concrete behavior.
Thank you. So a question perhaps for Athena, are you considering an LCA analysis of the materials that are being produced and studied?
Yes, we are trying to get as much information as possible on the upstream side of things. So during the production, the manufacturing, the calcining process of the clay, so the energy consumption, as well as potentially any essentially chemical emissions during the calcination process, in order to take those into account as part of the embodied emissions associated with the calcined London clay, and when comparing with other cementitious materials.
Well, that links very well with a follow-up question or a comment from one of the attendees that mentions that essentially you have same emissions from a GGBS cementitious blend compared with, for example, the ones you are producing, because the calcination of the clay goes up to 800 degrees, sorry. Have you done any sort of calculation if there is any sort of CO2 saving when we use these spoils as SCM compared with other ones?
That's a brilliant question. And this is the one we actually had to tackle in order to have people understand the value in carbon terms and get some funding for this project. Susan, Frank, feel free to jump in wherever. I'll give it a go, and then please feel free to add to it. So when we're isolating, let's say, a concrete sample, actually GGBS will always win on the simple, pure basis that GGBS, for instance, is a waste product of a different industry. And the way things work, it is therefore essentially not assigned any emissions through the iron making process, which is the actual process it stems from. So it comes out as a waste, pretty much emission-free, if you like, and it comes with very minimal emissions, embodied emissions associated with it because of the marginal grinding processes that are required for it to get powdered for use in concrete mixing. Calcined clay, as rightfully noted, it comes with high embodied carbon, but we're looking at the bigger picture, and in the grand scheme of things, of global construction growth, of depleting resources, and particularly those that are associated with steel making, iron making, so essentially GGBS. So we have, as Frag also noted during the presentation, globally, we have depleting stocks and limited availability more and more as construction grows, and also at the same time, in parallel, the demand for more sustainable, more low carbon alternative growth. So our current, let's say, ammunition, our current solutions do not suffice to essentially provide low carbon solutions to meet the global, the wider demand. So the concrete world is in dire need to explore solutions in that area. And this is one of them that can feed into the tapestry for overall decarbonization of the concrete. But surely Frag and Susan are technical experts in terms of it, so may have more to add.
Perhaps from my point of view, one of the beauties of this is this is a local solution. So it's not just embodied carbon in the manufacturing process of the SEM per se. It's also all the environmental savings and encompass the fact that it doesn't have to be transported. It can be, it's getting a waste that is causing a problem, like we need to landfill it, we need to do something with this soil. It's getting this and converting it into a beautiful resource that can be utilized effectively within the cycle of the infrastructure project. So it's almost like a zero waste type alternative. So I will say also, we need to think not just about CO2 emissions or this carbon tunnel, we also need to think about the entire sustainability impact of all the different activities we do, particularly with these major infrastructure projects. I don't know, Frag?
Yeah, I think you covered all the important points, and being aware of the time, perhaps we can just say that if we had infinite GGBS, that would be amazing, but we don't. So we need to find credible alternatives, and this is more and more important for big projects that want to establish secure and supply.
Just one last point from my end, just to kind of wrap it up from purely the carbon perspective. That's only one strand of the sustainability story, of course, this isn't rightfully noted. GGBS will always win in embodied carbon terms compared to calcined clay. However, we need to bear in mind that calcined clay is significantly lower in terms of embodied carbon compared to traditional Portland cement by over 50%. It's currently, our estimate is that it's around about 70% less carbon intensive than cement. So this is a very important improvement. That was it. Thank you.
Brilliant. So thank you very much, everyone, for attending this webinar. As I mentioned before, the recording of this presentation will be made available next week and will be shared with all of you. So I will also like to take the opportunity to publicize our upcoming webinar organized by the Circular Economy Center. So it's on the 22nd of November and is on waste and the circular economy in the next UK National Infrastructure Assessment. So we look forward also to welcome you in that webinar. And well, thank you very much, everyone, for attending, and have a good afternoon.